Okay, welcome to Michael Bisbano's master's thesis presentation in defense. Michael's been working really hard for about a year on an active sonar, following some things that he learned in class and with Professor Gendron and myself. The presentation will be probably about 40-45 minutes. I'd like you to hold your questions unless there are clarifications, or maybe if you can't see something and need a quick explanation. And then there'll be plenty of time for questions and answers. And then we'll ask you to step outside the room where we will dive a little deeper with more formal and in-depth questions about Michael's knowledge of the subject. So that's it, Michael.
Great. Well, I'd like to first thank everyone for being here. This is been working on this for a while. I'm glad to finally show some of the things I've learned and some of my results. Again, my topic is active sonar localization with acoustic spiral waves. My advisors are Dr. David Brown and Dr. Paul Gendron, and my committee members are Dr. Brown, Dr. Gendron, and Dr. Lee.
A little louder.
Okay. So first thing I'm going to do is go into some background motivation. What is acoustic spiral wave? What is active sonar? Why do we want to do this as opposed to conventional methods? And I'll break down some of the modeling of this active sonar, some of the parameters, constraints, variables that we use, and then go over some important equations and derivations I've done. And then I'll show you some of the tools I've developed, be it my toolbox. I've coined the Spiral-Wave Active Sonar software toolbox, and then some of the hardware I've developed, some simulations I've run, show you the results, and then I'll go into experiments that I've conducted and show you those results as well. Then we'll take a step back, look at some summary of this, applications, benefits, drawbacks, and then further work. So without further ado, we'll get right into it. So what's an acoustic spiral wave? That's a key topic in this presentation. Oh, let me hide this. So an acoustic spiral wave is a wave that propagates in the horizontal wall. It spreads omnidirectionally with amplitude, but the phase front diverges as a spiral in the horizontal or bearing dimension. So that phase front varies by 2 pi radians or 360 degrees with 360 degrees of bearing angle. So we can see here in this this fundamental equation, I have the arrow pointing to phi there. Phi is the bearing angle in spherical or cylindrical coordinates. So we can see it's just a exponential or complex exponential sinusoidal function with some vertical beam pattern that varies with time normally, but it varies in the phase front 2 pi over 2 pi radians. So throughout the whole of this talk, I'll be using mostly spherical coordinate system. And whenever I say phi, that is always the bearing. That's always horizontal. And then theta I use for vertical elevation angle usually. And then range is just radial distance. So there we go. So here's some background. A long time ago, in the 40s even, we were already using spiral waves for navigation. Now, that was for aviation with RF signals, but these two pictures here, the top one being taken actually at Logan Airport just a week ago or so. Yeah. No, yes, sorry, TF Green. These arrays of antennas, you can see the circle. There's maybe an antenna placed every 5 degrees or 10 degrees, probably 36 antennas located around, and they can phase that array to create a spiral wavefront. and they co-locate that with an omnidirectional antenna in the center. And now they can provide navigation information for aircraft just with the conjunction of a spiral wave, which has a phase front that varies by 2 pi with bearing, and an omnidirectional wave, which phase front doesn't vary with bearing at all. So they were using this for a very long time. They started decommissioning them in the early 2000s because we have GPS now. GPS is fantastic where RF propagates, but underwater, we don't have GPS. So spiral waves are still a very valid method of navigation or active sonar. So what this work is doing is building off of previous work by Ben Dzikowicz at the NRL, who's showcased previously that you can navigate and even do active sonar with spiral waves. I'm building off of that, trying to reevaluate, reaffirm that this is possible. And then really I'm focusing on developing tools so that anyone could try to understand this more and maybe implement it in the future. We want to make this happen for real. So that's where we're coming from. That's why we're doing this in the first place. Now, it's also important. There are a lot of ways you can make a spiral wave. You could have an element that's actually shaped kind of like a spiral in shape, and that could create a spiral wave, but that's very narrow band. You could have a phased array with a lot of channels, kind of like the RF approach for airports, but that's a lot of channels. You've got to drive. So that's a drawback. What we do is we use 2 orthogonal dipoles, and this method of generating them means we only need 2 quadrature signals, an in phase and a quadrature, 90 degrees apart. And when you drive 2 orthogonal dipoles, one with a cosine of phi and one with a sine of phi amplitude, directional factor, the conjunction of those together creates a acoustic spiral wave. And it's been, shown in previous works by Dzikowicz and all, his collaborators that works. You can create a spiral wave with that. So I was lucky enough to be able to borrow the same transducer used by Ben Dzikowicz from NRL to actually do this testing. So all the work I'm doing in simulation and in experiments is done using this method, the quadrature orthogonal dipole method of generating spiral waves, which is really convenient because to make a spiral wave, you only need 2 channels of signal, 2 power amplified signals. So right here, this is a animation made by my colleague Avery, which shows the conjunction of the 2 dotted and dashed lines are the cosine or quadrature channel, and then the sine in phase channel. And when they're added together in time, you see the solid lines drawing a spiraling dipole, which is essentially how the spiral is made using those 2 orthogonal dipoles. But moving on with that, we've shown that you can have a spiral wavefront with that orthogonal dipoles, but there's no such thing as true phase. You need to have phase in reference to a ground truth. So we have to transmit both an omnidirectional pulse and a spiral pulse together, spaced separately in time, so that you can use the omni pulse as a baseline to compare the phase of the spiral pulse to. So right here in this figure, we're showing an omnidirectional pulse, and then the I and Q channels of the spiral pulse to drive the spiral pulse, and then another omnidirectional pulse. And I'll explain a little bit more in detail later why we're doing 3 pulses with I call it a spiral sandwich. But in this bottom plot, we're showing the generated signals of the I and Q. You can see they're 90 degrees out of phase, the quadrature, and we also have to do like a 2-key window on the pulses we're sending, so that we're not just hitting impulsive for the cosine channel. That's fine. You don't have to window it because it builds up. It starts at well, the sine channel starts at 0, but the cosine channel would start if it's 90 degrees off at 1 or -1, and that's not, a transducer is not going to love that. So we 2-key window both of them to build up to our peak response, and then window it back down. But 3 pulses is due to some variation we would see if a target or the platform that this is mounted on has any radial delta velocity. If the target is moving radially towards the spiral wave beacon, then the spiral pulse, since it's transmitted at a known time delay after the omni pulse, but the target is moving towards you, the two pulses will return closer together, and that will behave like a phase shift in the bearing, which would skew your bearing estimation results. So by having the third pulse there shown now this time in the bottom plot with the black first pulse and the green second omni pulse, using the conjunction of those two, you could match filter detect the first omni pulse, match filter detect the second omni pulse, and determine the time difference between when the second pulse should have arrived and when it did arrive due to Doppler shift and moving targets, and then correct for the Doppler estimation of where the spiral pulse slid and correct for that bearing error due to it. So you could use the same match filter to detect the range from the first pulse return and Doppler shift, finding the second peak in your return there. So you could argue with the two pulses, you could determine that Doppler shift or that target velocity just using frequency-based methods of Doppler detection, but that's that's more computationally intensive than just a match filter, and you also need to have a high SNR to get good Doppler results. So this method really simplifies the target radial velocity estimation and simplifies the process of correcting for any bearing error due to radial velocity changes. So here's a very basic model, taking a step back from that Doppler correction. This is just assuming we have a stationary target. We've got the hydrophone input. We've transmitted a pulse. We know what the pulse was. It's we did a LFM or a CW or a BPSK. We transmitted that pulse. We did the omni pulse, spiral pulse, and an omni pulse again, or just an omni and a spiral. Those go out. We know when they were sent, their frequency, all their characteristics. Now we've started a timer. We're counting, we're sampling. Hydrophone input comes in. We have to obviously A to D, so we can do digital processing. And then we match filter that. We look for the peak of the match filter that corresponds to the first return from a target. And that gives us a two-way travel time for the target. We compensate for the group delay of the match filter. And then we can resolve the range of the target using the simple, assume constant velocity and sound about 1500 meters per second, divide by 2 because it's a two-way path. And there you are, you have your range. And then we can take that range and the output of the ADC and go take that raw signal and sample it when the reference return came and move over one spiral delay for when the spiral comes in reference to the omni return. And we can take that and do an FFT over both of those windows and pull the phase bin of both of the peaks from the same bin on each of them. So it's coincide. And that peak phase, which we take, directly encodes the bearing of the target just from 2 FFTs, the match filtering to get when the range came. And there we are, we have the phase difference. Radians to degrees to report it in degrees for your sonar operator, because people don't have as intuitive a grasp of radians. And there we are, we have our range and bearing estimate, and that works great for stationary targets. So there it is, that's all you need. The signal processing there is bare bones. You can do that with a cell phone from the early 2000s, likely. So, but really there's more to it than just that. You need a high enough SNR. So your source level has to be high enough, and characterize source level with the TVR of the projector and the drive voltage. So a TVR at peak response primarily. Then there's the transmission loss, of your channel. You could say it's spherical spreading and do 20 log 10 of the range. You could say it's cylindrical spreading and do 10 times log 10 of the range. You could do a piecewise function where it's spherical until it becomes cylindrical. I've used a kind of approximation of some channel. I'm operating in generally shallow water is my understanding. So I'm using 15 log 10 as a placeholder here, but really it could be, you know, a more complex understanding of your actual channel parameters. That's your transmission loss. There's target strength, which is, you know, the ratio of reflected intensity off of a target in comparison to the intensity impinging on the target. So that's usually for the small targets I'm working with, that's usually very small, like minus 30 dB or so for what I'm testing. But that scales with your target, its geometry, the actual aspect of it that it's oriented. So that's a really complicated problem in itself. But for me, I'm just using a spherical source estimate, you know, a point source reflector. Noise level, I'm assuming we're ambient noise limited, not electronic noise limited, not reverberation limited. So I take the ambient noise level. We're operating around 60 kilohertz. So go on this plot. This is Wen's curves, published in a while and then redone with a more recent paper to put color on here and make it easier to read in my references. And so we go on this curve, find our frequency. Our bandwidth is small enough where I can say the slope on these curves at 60 kilohertz, which is somewhere over here. Slope on these curves is low enough, and my bandwidth is shallow enough that I can just say it's a flat distribution in frequency, close enough to that. At least that's what I do now. So that's my ambient noise level, and then you have to add in dB how much bandwidth your front end is taking up, and that adds to your noise as well. So there's your noise level, and then the directivity of the receiver is also a factor. When you're receiving, if you're focusing only in a smaller sector, you'll get relative gain in that area you're looking. I'm showing the equation for continuous line sources directional directivity index, but realistically, it varies a lot on your receiver and its dimensions. And this is just showing, you know, it depends on the physical shape and size of your transducer for receiving your hydrophone. So another great topic of interest that is, you know, the cause of many research papers and theses in active sonar is what pulse shapes. It's a huge variation. They can change your, you know, the ambiguity function of your pulse shape changes your performance drastically. So CW, it's great for Doppler detection. You've got very narrow band, so your Doppler detection is great, but your range resolution suffers because it's coherent over the entire length of the pulse. LFM is a good approximation that's used a lot to do some pulse compression, tighten up your range resolution, and you maybe get some coupling between Doppler resolution and range. A Doppler shift will look like a range shift and vice versa. BPSK is used a lot with like minimum peak side lobe and Barker codes, or, you know, stuff like that to create pulses that are, you know, pulse compressed. They have some bandwidth, but it's BPSK digitally coded. You could drive that with a, you know, a FET circuit or something. And then after reading a doctoral thesis by one of Dr. Buck's recent students on generalized sinusoidal frequency modulation, which essentially looks like a linear frequency modulation pulse in the spectrogram, I decided to also try and look at sinusoidal frequency modulation and generalized sinusoidal frequency modulation, just to see, you know, if I can apply that, you know, recent doctoral thesis on my work as well.
Who was that?
That was David Haig. So in any application for sonar, it's up to the implementer of the system to determine their waveform and how they use it. But I'd like to try and at least explore a few of these and see their benefits, sometimes generating a CW or LFM is easier than a BPSK. Sometimes it's vice versa if you're using a lot of DSP. Generalized sinusoidal frequency modulation might have a lot of benefits, but it's much more complex to generate. So there are a lot of trade-offs with all this, and really it comes down to the end implementer. But there are things I tried to look at least a little bit. So here's some more detail on the Doppler shift effects. So for monostatic platform, the change in frequency returning on the monostatic source, monostatic meaning the projector and receiver are co-located there next to each other. They don't have to be the same element or same transducer, but we assume they're close enough to each other such that any outgoing wave reflects off a target and comes back to the same spot for our receiving. So that's monostatic. There's also bistatic or polystatic or multiple locations, but I'm only focusing on monostatic here. We know the Doppler shift off of a moving target depends on its relative change in radial velocity from the source and its location. It doesn't matter if it's got any velocity parallel or sorry, perpendicular to radial axis, because that's not creating any change in distance. That's the change in distance that creates Doppler shift. But if we do some math, we can calculate the change in the target's radial distance between the reference and the spiral pulses. Since we're sending the reference, waiting, and then sending the spiral pulse, that spiral delay creates a delta in the target's actual radius when we actually receive the reflection. So that change in radius, when those two pulses arrive, creates a change in the spiral phase for the reflection. So this delta beta, due to sub delta V for change in velocity, goes by 4 pi and on the change in radius over lambda. So right on the right here, I'm showing a quick little calculation I did in MATLAB to showcase that for a target moving at 1 meter a second, which is relatively slow compared to some of the targets out there. And if it's a torpedo or something, it's humming much faster than that. And a center frequency of 5.7, 57 kilohertz, spiral delay of 0.6 milliseconds. So that's the delay between the omni pulse and the spiral pulse. The delta F or the Doppler shift in frequency is only 76 hertz. But the delta range is significant enough that the phase shift interpreted by the bearing estimator would be on the order of like 16 degrees, which is huge for a target that's only moving that small. And we could reduce this by reducing the spiral delay, but then by reducing the spiral delay, we might also have to reduce the pulse width, and that might reduce our actual power output. So there's a lot of variables here. And really, I found the best way to fine tune this so far has been to just experiment and rerun the simulation with different parameters and hone in on what's working best for any given situation. So another interesting case that can occur with spiral wave active sonar is if we have multiple targets that are at the same range. If you're doing conventional, phased array bearing estimation, and you have multiple targets that come in at the same range, you might be able to detect that if they're at different bearing angles but same range, and you're processing each angular bin or whatnot when you're doing your phased array processing, you can maybe see a return from one direction and the other. But for a spiral sonar, especially if they're 180, the two targets are at the same range and 180 degrees apart in bearing, the omni return will add together, but the spiral return will cancel. So there's definitely some interesting effects here. And really, this limits your processing. Unless you get really complicated with it, you're really limited to only detecting one target per range bin. And I'd say the range bin is on the order of the entire pulse train's length. So if you're doing an omni, then a spiral, then an omni, the entire duration of that needs to be your range bin is dependent on that, not the order of one individual subpulse, but the length of the entire pulse train. So, this is shown here for any order of n targets. If they're all around the same range with some slight variation within a range bin, these summations are showing the omni return and the spiral pulse return, and the spiral pulse return just has that extra bearing component here with the e to the negative j phi sub n for the nth target. So if they're 90 degrees apart, they might add together and look like they're one big target 45 degrees in the middle, a little smaller. But yeah, there's a lot of interesting behavior that can happen with multiple targets at the same range. So I just wanted to showcase that here. It's not always simple processing. But now some of the hardware, in the CIE, we have access to this TiPi system. It's I think a Swedish company that produces USB oscilloscopes and function generators and whatnot. They're great pieces of equipment, high resolution, high sampling rate. The clocks for the wave generators and the oscilloscopes are synchronized you can plug in multiple units, and they have a synchronization bus. So the clocks are everything is sampled. The wave generators of the oscilloscopes are sampled simultaneously every time. It's a shared clock, which is great. Problem is we're using MATLAB to interface with them, and the MATLAB library written for this TiPi software doesn't allow multiple function generators to be triggered at the same time. You need to enable one, then the next. And that delay can't be known because it's MATLAB deciding when to trigger one or the other. So that's a huge problem. If you want to, drive 2 signals at the same time or 3 signals at the same time, and they have to be 90 degrees phased, and you have variation due to MATLAB's processing time, iteration by iteration, that's terrible. So luckily, I was able to look on the back of this TiPi unit, and they've got this DB9 connector, which is fantastic. I recognize that right away, and say, oh, what's going on there? So we pull up the manual for this TiPi device, and pins 1, 2, and 3 are external input-output triggers. You can control their behavior in software. So, well, what if I only trigger one TiPi through code, and that TiPi will pull an external trigger low, which tells the other TiPis to start synchronously. And, I was able to do that. So now in software, I just have to start one TiPi, and whenever MATLAB decides to actually start it, all the other TiPis for the oscilloscope, clocking the oscilloscopes to gather information and clocking the waveform generators to generate signals, that all happens at exactly the same time. So problem averted. I can use the existing hardware and get reliable phased driver signals. And the receive is also clocked the same way. And then develop some hardware. If I want to use a monostatic source, I'd love to use the same transducer as a transmit and receiver. Then it's a really monostatic source. I don't have to co-locate a hydrophone and a projector. I just have one transducer that I use for both. So I designed and implemented a low-cost TR switch for a transmit receive. It'll switch between the two. And it's just using a passive threshold detector. When the passive chip detects a voltage over 2 volts, it opens up under 20 nanoseconds of response time. And then when it detects that the voltage has fallen below 2 volts, it will close with like a 15 ohm shunt. So I made this circuit. You would connect it as such that your drive circuitry would go into an input that's coupled with a high impedance coupler, so that small signals from the hydrophone on the return don't try to backfeed and drive the transmit electronics. But the transmit electronics are piped through that coupler to the passive TR switch, which will open up when you're transmitting and protect the preamplifier electronics, but still be connected to the transducer. You can drive your transducer. And then on the receive, when you're not having the high voltage, the passive TR switch is closed, and the small signals coming out of the transducer are only passed through to the preamplifier because the high impedance diode coupler is blocking the small signals from going to the transmit circuitry. So this little circuit BOM cost is like, I said $30, it's really like $23. And you know, the preamplifier is rated to like 0.9 nanovolt per root hertz. Okay. So really noise-free circuit. So, you know, you can bring that into the receiver and, you know, around $30, you get a great TR switch. One thing to mention there, the tolerance on the passive switch is 100 volts peak, plus or minus. We'll get back into that later and why that was a problem for me. Then I did a quick simulation, well, not a quick simulation, a very long simulation in a toolbox called K-Wave, which allows users, it's primarily made for like medical ultrasonic applications for phased arrays and whatnot. But it allows you to do time domain simulation of 2D and 3D fields. So I created a model of that multi-mode quadrature dipole cylinder in this using pressure and velocity sources. You specify what time they move and how much, and then place hydrophones at 1 meter radius every 1 degree bearing. And this plot on the right is showing the phase difference estimated between an omni pulse and a spiral pulse created in this simulation. And we see that it follows a linear curve of the received phase as a function of the bearing angle. So, you know, just the simulation proving that, you know, one, I can simulate this acoustic field for further use, and two, that, yeah, this aligns with our theoretical beliefs and what others like Ben Dzikowicz have found for the spiral phase front. Then this is the real bulk of my work here. This is my Spiral-Wave Active Sonar toolbox. This suite allows me to both run simulations of the environment and talk to the Taipei hardware in the same system. I can set amplitudes I'm driving, specify where targets are for simulation, or tell my processing where they are for ground truths in a real environment. Specify frequency, bandwidth, pulse width, spiral delay, pulse shape, pulse chain type, any blanking on the signals, pulse delay if I want to change how I'm doing, you know, time varying gain or bandpass filtering. All this stuff I have the ability to do within this software. So it's a great starting point for any you know, push into research on this topic. So if I were to run a simulation or run an experiment, I would essentially, I'm going to walk you through what I would do. First, I hit generate signals, and this will generate the omni and the spiral pulses and show me them to make sure, you know, I've got, you know, my timing correct and everything looks correct. And then it's actually going to transmit them. And the top two plots are showing the voltage monitors of the power amplifiers. On the outputs of the power amplifiers, these are the voltages coming out, right? So we can log them. And then on the bottom is the receive channel from the hydrophone. And you can see right when I'm transmitting here, the time axis is the same on the top two plots, but it's different on the bottom. The bottom plot, you can see those two strong pulses, and that's the direct path coupling, or the shouting in your own ear of transmitting into yourself. It's your self noise. So this orange line on the bottom plot is my blanking window. I essentially multiply everything in the receive signal by 0 until I'm past my shouting in my own ear, you know, method. And then you can also see in this picture, which we'll get into more later, but the two small pulses after that are the actual return from a target. So I look at the received signal, and then here's the output for my match filter. I actually had 3 targets there. You see the green triangles are drawn where I'm simulating the targets to be in the space. And these plots are the match filter outputs. For a little bit, I was playing around with doing a different match filter for the reference and the spiral pulse. That kind of got tossed aside, but the plots are still there. Really, what you're looking at is the top one, the match filter pulse on the reference pulse. So you can see the returns for omni and spiral on all 3 of these targets out there come at different times. And here's where the processing in the simulation in red has placed the targets to be, which, within this plot is, a good visualization of, here's my acoustic field, here's where my targets are, and, here's where my results, here's where I thought they were. So it's a great way to benchmark and evaluate different, processing schemes and different signal generation types. So that's my Spiral-Wave Active Sonar toolbox. Here is some simulated results of me replicating tests I did in the SMAS tank, which I'll show later, but I want to show simulation first because simulations are always perfect. So on the left here, well, first in the center, that's showing all my sonar parameters. There's a lot there, and I'm simulating a target strength of -32 dB, which corresponds to what I calculated the target strength of the actual target I used to be. Ambient noise level around 30 dB, which in the tank is low, but I need to put some noise in here to compensate for the electrical noise and low signal level I was using in the tank. And then simulated noise level when I add in the bandwidth of 6 kilohertz, around 67 point something dB. So then I'm simulating a target that's staying at the same radius because the range estimation is simple. That's time based. What we're really focusing on is the bearing estimation. So I am rotating this target through bearing every, I believe I did every 3 degrees here or 5 degrees steps in bearing, same range every time. And on the right, we can see the red marks are, every time a return was found, that's where the target falls. So it follows a circle, which is good. That's what I was simulating it. And on the left, we're seeing the black line is, an ideal linear line between 0 and 360 degrees. Blue curve, which is the one with the actual variation, is the bearing estimate I get when I unwrap it. And then when I do a line of best fit on that bearing estimate, I get, shown here in the center box, the mean square error of the range is 0. The root mean square error is 0. And the bearing correlation coefficient is 1, which is great. It's simulation. We'd expect that. We'd hope that. So that's with LFM pulses. Generalized sinusoidal frequency modulation is also what I was able to test for this. And again, range error is even more close to 0, and bearing correlation coefficient is still 1 for simulation data. Same everything else for parameters. Now, here's experimental setups. First tried to do simulations in the small test tank available at the CIE. It's about 1 meter by half a meter or so, maybe half a meter deep. Very small tank, and at my frequency, 60 or so kilohertz, the wavelengths maybe 2.5 centimeters. So for me to get the actual pulse lengths out there, it's I get a couple of cycles before I'm getting reverberation and reflections from the walls. So that tank's a little too small for active sonar. But I'm just showing here in that picture on the left that you can see all the tie pies, power amplifiers. On the right, it's zoomed in more. I'm using a Instruments Inc. L2 for the Omni channel, and then 2 Crohnheit 7500s for the I and Q channels. On the bottom here, I'm showing theoretical directional factors and beam patterns for the spiral wave transducer I'm borrowing from the NRL. The theoretical, it's assuming continuous line sources, which isn't great, but just to get an idea, the black line is just one of the Omni elements. Green line is just the spiral element, and the red dotted line is the array, effective combination of the array and Omni elements total beam pattern or directional factor. Just to give an idea, this is in elevation angle. So obviously, like I said, the HF tank was too small for these tests, so I went to the SMAS tank, the underwater test facility. That tank's about 8.5 meters long, 6 meters wide, about 6 meters deep. And if you place your target and your spiral beacon as close to center of the tank as possible and space them, such that you get as much time for your return before tank reverberation and reflections from the walls get in, you can get a good test for a range of like 1.57 meters. with everything at 2.9 meters depth, which is half height. This picture in the top right is showing the target I used. It's a little steel cylinder, 4.7 centimeters diameter, 3 to 4 centimeters high. And that, when I computed the target strength for that using a simple, ballpark equation, that was around minus 32 dB target strength. So that's why in simulation I use that target strength. But using the same acoustic signal parameters as in the simulation, and these are some of my results. This animation on the left is showing for each bearing angle sampled. The blue is the omni return that I windowed over, and the orange is the spiral return that I windowed over. And you see, as we rotate the bearing angle, the orange return is sliding to the left. And that's directly, corresponding to the bearing angle. That's the phase. And in the center plot, we see, again, the black is the ideal 0 to 360 degrees linear curve of what we would hope the bearing response to be. Blue is our estimated bearings when we unwrap them. So we can see there's some eccentricity on it. I'll get into that a little bit more, but when I fit a curve, the correlation coefficient is still approximately 1. MATLAB rounds up. So it's working. It's definitely working, and it can only get better. The top right is showing the same returns as before, and you can see there's like clustering on the 0 and 180 degree nodes, and it's more sparse on the 90 and 270 degree nodes, and that corresponds to the eccentricities we see in the phase response. So that was with LFM. Ran again with generalized sinusoidal frequency modulation, and again it worked. The bearing still had the same eccentricity as before, and the range error was much less, which corresponds with simulation results, and the generalized sinusoidal frequency modulation's ambiguity function. It's generally better for range. For this, we were only able to sample with 15 degree steps. We were manually rotating because the rotator makes too much electrical noise. I forgot to mention that earlier, but the rotator at SMAS makes too much electrical noise for us, and it's in band. So I had to have my friend Avery manually rotate the transducer for every 5 or so degrees, and then to save time for GSFM tests, we had to rotate 15 degrees. But we made a little, essentially a sundial, and rotated to that. So there's some human error involved in these results as well, for sure. Now, to address that eccentricity we see, here's just a measured phase response of the spiral beacon transducer we're using, measured one way. This was when measuring a beam pattern of this transducer, we can pull out the phase information, and we see that there's a very similar eccentricity in our results for the spiral sonar and for just measuring the phase response of the transducer in a one-way test. So that implies some of the bearing offset, one, it could be corrected for because it's consistent, and two, maybe this bearing error is something to do with the mounting of the transducer. Maybe it's canted a little bit, or it could be due to the physical transducer itself, if there's any manufacturing, slight defects or whatever. But again, that's showing that the eccentricity we're finding is not, unique. So I'll do a quick summary. Benefits of this: it's a small aperture. The thing's, yay big, as opposed to an array probably about this big for full 360 degree bearing coverage and very, very simple signal processing. You only need 3 transmit signals and 1 receive signal, and you can do that processing on the fly on a lot of really, really cheap hardware. You can track multiple targets at the same time as long as they're at different ranges. The processing is there. Obviously, if you get too far away, you're transmitting omnidirectionally, you're attenuating yourself. But you could also use the same signals for active sonar that you're using for navigation. So you could provide navigation information to a bunch of autonomous vehicles and also track their location with the returns at the same time with the same signals. Some of the drawbacks, it's not a directive transmit. So if you want directive gain to hit a target far away, maybe this isn't for you. Driving the phase signals accurately at 90 degrees is a challenge. If you were to use higher order transducers, maybe 3 or 4 dipoles, that could be even harder. You have to generate, 120 degree phasing. Or if you're using a phase array to make the spiral, then you have even more channels to drive. So that gets challenging. But with using the simple quadrature dipole solution, that gets, that's reduced. It's a very simple 90 degree phase shift. Some bearing accuracy concerns for a high Doppler target, but we think that can be corrected with the third pulse there added to encode the target's velocity in just time delay. So some applications I mentioned earlier: autonomous underwater vehicle swarms, communication navigation systems, tracking divers, and also providing navigation for divers. This is up at 60 kilohertz, and it's been shown that that's, you can operate pretty high signal levels while safely, with divers around, as long as they're aware of it and they're, wearing neoprene head covers, they can safely be exposed to this frequency range without suffering any injuries. Could be a very cheap alternative for collision and obstacle avoidance on water vehicles, or in the air. You could also implement this. You could do a quick scan for biological, entities, a whale or whatnot, around your ship before you conduct like a high power naval test or something, where you want to do a low power test to make sure nothing's out there before you boil water. And then like a high-end coastal solution where you could just airdrop these along a coast and have, a really low cost, low power, low maintenance array of monitoring systems. So future work: do more measurements, reduce the instrumentation noise, fix the rotator so it's not screaming into the void. I'd like to use some step-up transformers. The TR switch I built has that 100 volt limit. Problem with that is, to get a good reflection off of that minus 32 dB target, I had to crank the input up, and I'm at my 100 volt limit. So I ended up having to co-locate a hydrophone just next to the receiver. So with that hydrophone there, I would have preferred to use the same projector receiver in the same package, but I had to co-locate a hydrophone. That way I could bypass my TR switch and drive the voltage up more. So that would be good. If I use some step-up transformers, I could have that after the TR switch going towards the transducer, which would step down the receive signal, but it would step up the transmit. So then I could still use the same TR switch and maybe get the same results or better with one projector receiver unit. I'm thinking I could maybe use different pulse waveforms within the same chain. Maybe do GSFM for the Omni and Spiral, and then the third one could be CW to give more Doppler information, just because it should be a fixed tone. So when it comes back a little higher or lower, you have great Doppler resolution on that last pulse, because it's not really encoding any range information. So there's a lot of work that could be done with playing around with different pulses. You could maybe spatial filter in the vertical axis and determine the target's depth in the water column, while maintaining the spiral bearing estimation for range. I'd love to calibrate the source with have a ground truth of true north, because right now it's 0 to 360 degrees relative to wherever it's facing. And if it's floating around in the water, well, there's going to be some error there as well. So true north calibration, Doppler detection, I kind of mentioned that as well. And then maybe some particle or Kalman filtering for tracking the target states through time and improving your resolution or accuracy, precision on the target. Communication would be great if you encode information in the same pulses used for active sonar. Then you can talk to someone, encode information in the spiral. There's a lot of potential work with that. And also, my colleague Avery is working on using more than just a quadrature dipole. How about a tertiary or three-phase system? and there's signs that that would increase your signal bandwidth and maybe your transmit level and have better bearing resolution. So he's working on circuits that would be able to drive that, which is huge because right now, just generating 2 quadrature blocked things isn't easy. So that's my future work. Any questions?
Questions?
Well, Michael, that was certainly expansive. I don't know if you can hear me.
Yeah, I can hear you
Can you hear
correctly.
me? Okay. I thought that was a great presentation, and I learned a little bit. And thank you for going over everything you've been working on. Just a few quick points, or at least one that's pretty low hanging fruit. You mentioned on slide 22, 23, maybe 24, this source of bearing error, and you alluded to that. Well, it seems to be systematic because when you just tested the transducer, you also saw this. Uh, from my experience, this is something that can be corrected easily, and most often it's due to not being in the direct center of rotation as you're rotating it. And
Yep.
so it could be the pipe, the pole is a few millimeters non-concentric to the axis of rotation. And so when we're doing careful, let's say phase measurements, we typically correct for this in processing.
Sure.
And it often looks like a sine as a function of angle, which kind of looks like what you're measuring. So how would you go about correcting that? What data would you look for to make that correction?
So if you were able to measure,
Just briefly summarize.
yeah, to repeat it so everyone can hear, this eccentricity we're seeing, or error in the bearing, it seems like something that's correctable, and it's maybe due to how the transducer is mounted if it's off axis from the center of rotation. How would I correct for that? There's definitely what I first see is the slope is always positive on this. So I think you could fit a curve to this and then draw it to a linear curve. But beyond that, you could just have a calibration file of your transducer setup and how it's mounted, and then fit the curve to that, and then pull your points back to where they would map to on a linear 0 to 360 sweep.
Yeah, so if you had just an omni element transducer and you're sweeping the angle, so you're taking a beam pattern, what would you expect the phase to look like?
On an omni?
Yeah.
If I'm rotating the omni source, I would hope that the phase stays constant as I rotate it.
Right. So if you measure something that looks sinusoidal, or it'll have some offset, some peaks at some angle, you can do a curve estimate on that, and that would be a good indication of your error. So if
Yeah.
you have measurements, and these measurements are setup specific, right? If you were to reinstall the transducer, you might not reinstall it the same way. So if you have omni data, magnitude and phase for this transducer as a function of bearing angle, then you can further correct the data that you've presented, and I'm sure it'll be a lot tighter.
Absolutely. Yeah, that's a great idea. Thank you.
I mean, we could have conversations for hours, but I'm not going to do that. There's just, I think, maybe one or two more quick points. What if you have targets? So in your scenario, you had, I forget which slide, but you had 3 targets, and then you showed the time series, and they were separated in time. Yeah, I think you passed it. So what if the targets were at the same range but at different angles? How would you go about untangling that?
Yeah, that's a big problem. I haven't fully wrapped my head around it, although I have done some work to derive how I would expect those returns to show up. This bottom 2 equations here are how I would expect the reference return to behave, and then the spiral return to behave for any n targets that are around the same range. If they're perfectly 180 out of degree, and you see a strong omni return and no spiral return, maybe you can say, well, I've got two targets, I know they're there, and they've canceled each other, but I have no understanding of the two spiral returns. If you maybe used maybe a 3-axis accelerometer receiver or something like that, you could maybe do some underlying information. Maybe if you had multiple of these and then did kind of like a ultra short baseline with 3 of them to do the receive, but that's getting complicated and defeats the purpose of that.
Corey,
Yeah.
I'm going to ask you to hold your questions. You
Sure,
can stay
sure.
on afterwards in the defense or any other questions? Mr. Bispano, you've been wondering what he's been doing all night, right? Peers, colleagues?
Hi, David, where is the defense? The physical location?
212.
212. Okay. So I'll be back. So when will be closed sessions? When will the closed session start?
In 5 minutes.
Okay, so I'll be there in 5 minutes.
Okay.
Okay.
Okay, Corey, you're welcome to stay on, Corey. But let's thank Mike. You did a great job. And if there aren't any questions, I'd like you to ask you to leave the room so we can do a deeper dive on the subject. Thanks for coming, Austin, Avery.
You want me to stop recording?
Yes. Thanks for coming, David.
Thanks, David.